Coming up next, an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of Astronomy. AFM Radio, AFM Radio, AFM Radio, AFM Radio, AFM Radio.
Hello and welcome to York University Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. I'll be one of your hosts this evening. This is Dr. Elena Hyde, and tonight I'm joined by Quentin Wayrich of previous episode fame, and of course we have a very special guest who I will introduce later on in the show, Dr. Rahul Kannan, who's come in to tell us about all kinds of really exciting stuff. So this is a very special episode tonight, and we are in fact broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. As a reminder, this is Science Night in Canada, where the lineup is all Canadian, starting with ourselves, York Universe, then on to Western Worlds, Quirks and Quarks, and Science for the People. York Universe broadcasts every Monday night at 9 p.m. local Toronto time, or if you prefer another time zone, Tuesday morning at about 2 a.m. UT. The York Universe production works in concert with our online public viewing program run by our amazing observatory team, which runs at the exact same time. That's right. That means if you are listening live, you can head over right now, go to yorku.ca/science/observatory and follow the links to OPV or online public viewing. Conversely, you can also just go to our YouTube channel for the Allan Carswell Observatory and click on it, and it is live right now, 9 to 10 p.m. local Toronto time. Our crew is showing all kinds of lovely images, maybe not live tonight because it's a bit cloudy in Toronto, but they are broadcasting this show and of course have an open chat so you can ask them anything you want. Our broadcast is powered by and in partnership with Astronomy.fm, the voice of astronomy. If you have any questions or comments or would like to tell us what you thought of the show, just email us at observe@yorku.ca. And of course we also are on the social medias. We have a Twitter handle of @York Observatory, on Instagram @YorkU Observatory, and Facebook @Allan Carswell Obs. All of our programs are free, but if you would like to make a donation, you can see that website, yorku.ca/science/observatory that I mentioned before. Our crew is monitoring the chat line over on online public viewing for any questions. And the current weather is, the weather in Toronto has been crazy. It was super hot yesterday and super cold today, so of course it's really cloudy and actually semi-raining. There's talk of snow flurries. We probably won't be able to open up the telescope domes tonight, unfortunately. So we're looking forward to sharing some beautiful stock imaging over on OPV. How's the weather up in your neighborhood, Quentin?
Very dark. It was raining earlier when I was taking my dog for a walk. It seems to have stopped that now, but I have a feeling it's going to start up again at some point tonight.
Yes, indeed. It's it's been, of course, not so great today. If you were out looking yesterday, it was quite a bit better. Unfortunately, we can't go back in time, but if you do happen to be in the Ontario region and somehow you do have clear skies, I would just like to point out that Venus and Mars are both pretty awesome just after sunset, the next quite a while, actually, the next few weeks. Venus is just getting a bit low in the horizon. It's about 25 degrees above the western setting, but it's been really spectacular last few nights. You might have seen something really bright in the sky just after sunset. There's a good chance that was the planet Venus. Have you seen it, Quentin?
Oh yeah, it was incredible.
Excellent. Yeah, it's a great one to start off with if you're just getting going on stargazing. And let's go ahead and hop over to our guest, Dr. Rahul Kannan. Dr. Kannan, how's your skies been lately?
Oh, I'm in Toronto as well, so.
So you're also dark and rainy.
Yeah.
Ah. That's
Well,
3 for 3. We've struck out. Sorry to hear that.
Yes, if it is clear skies, it's probably outside of our direct region. Maybe if you go up north.
My parents are out of the country right now. Maybe I'll ask them how their night sky is.
That's an idea. Yes, actually, I do have some colleagues in Australia, so it might be maybe I'll call them later, see how they're doing. All right, excellent. So we've got a little bit of an interesting program for you planned tonight, everyone. We're going to do a very, very quick little This Week in Space and Astronomy History section, because as some of you might have been watching, there was an almost launch this morning. Of course, SpaceX's Starship was hoping to lift off from Starbase in Boca Chica, Texas, earlier today. Unfortunately, they scrapped it. But, I thought it'd be fun to say, well, it's not just right now that we're looking at spaceships and launches. If we go back in history quite a bit, we actually have some interesting things happening around this date in history. So, Quentin, why don't I let you take us back to our first little This Week in Space and Astronomy history?
Absolutely. Yeah, the launch, the attempted launch this morning really puts me in the mood to think about other forays into the world of rocketry. On April 16th, 1965. So yesterday, and then in 1965, the Saturn V first stage was successfully test-fired for the first time at NASA's Marshall Space Flight Center. The Saturn V was, of course, the famous rocket that was designed to take us to the moon. This was the rocket utilized in all of the Apollo missions, as well as the rocket that put Skylab, the first American space station, into orbit. All told, the Saturn V consisted of 3 stages: the S1C, the S2, and the S4B. What this means is that the Saturn V was effectively 3 rockets stacked on top of each other, each of which had its own engine powered by liquid fuel, and each stage would fall away once its fuel was expanded, which reduced the total weight of the vehicle for the next stage. So the S1C booster stage included 5 F1 engines, which were capable of producing a combined 7.5 million pounds of thrust. The test was on April 16th, 1965, like I said, and it lasted a full duration of 6.5 seconds, and it met all main test objectives. And sure enough, only 2.5 years later, the Saturn V had its first full launch on November 9th, 1967. This was the Apollo 4 uncrewed test flight, which was a complete success. The Saturn V would continue to serve as NASA's workhorse for the next 6 years, through all of the moon missions that followed, with its final mission being Skylab 1 on May 14th, 1973. As of 2023, the Saturn V remains the only launch vehicle that has carried humans beyond low Earth orbit. But hopefully, that won't be the case for much longer.
Excellent. Yes, I think that we're all looking forward to more space capability, shall I say, in the next coming years. And of course, it's worth mentioning that despite all of our advances so far, the Saturn V is still the reigning champion of giant rockets until it is surpassed by something else. It has still the most successful launches, and especially the most successful moon sort of trips, shall I say? What do you call a journey to the moon? It's not a drive, it's a blast. So this, of course, reigning champion of giant rockets, as Quentin mentioned, is that 3-stage booster. It was primarily used in the 1960s and 70s, and it was absolutely massive. So this was 363 feet or 110 meters high. And even though the last one flew all the way back in 1973, it still remains one of the most powerful rockets ever. So the last Saturn V was actually a modified version that launched NASA's Skylab space station, actually. And smaller versions of the Saturn rocket were used to launch astronauts. And of course, if you wanted to, sort of compare it, it's not as massive as the spaceship, which they're hoping to, or sorry, Starship spaceship. I'll say that 10 times fast. They're hoping to get working from SpaceX, but it is still the record holder, so it deserves all of our respect and kind thoughts, I suppose. Of course, this being back in 1965 that they did that first test fire, and now we're in, gosh, what is this, 2023? Like, wow, we are in the future. So I'll go ahead and take it. Waxing aside, I'll go ahead and take us to our second item, which is I just wanted to point out that on this day in history, rocket launches allowing and all of that good stuff, we actually had April 17th, 1970, so a few years later on today's date, we had Apollo 13 returning to Earth, and Apollo 13 also used a Saturn V rocket. So Apollo 13, we have talked about before on this show, so I probably won't go into it in great detail. There is an entire movie about it called Apollo 13, but Apollo 13 was the 7th crewed mission in the Apollo space program. It was the 3rd meant to land on the moon, and the rocket did certainly get into moon adjacent areas, but it did not have a particularly lucky trip. Well, it was either very lucky or very unlucky, depending on how you look at it. But the lunar landing was aborted after an oxygen tank in the service module failed 2 days into the mission. So the crew instead looped around the moon and then returned safely to Earth on April 17th. And it was quite a bit of intrigue around this time because, why exactly this happened, how it was managed, and with this kind of mission, you also had a lot of different things happening. So it wasn't just the service module. They had sort of a routine oxygen tank stirring incident, I believe, that had some sort of damage, and of course the crew module systems had to be shut down to conserve remaining resources. So they had to actually use the lunar module as a kind of a lifeboat. The mission was very, very tense, and you had mission controllers working around the clock. There's a lot of stories back from NASA about people who really went above and beyond to try to figure out how they could actually bring the crew safely home. The lunar module was designed to support 2 people on the lunar surface for 2 days, and they had to improvise so that they could support 3 people for 4 days. So they had a lot of hardships. They had wet and chilly conditions. They didn't have enough water. I believe several of them arrived severely dehydrated, but they did actually make it back. And this was incredibly tense mission, made possible by the Saturn V. So I suppose that was both, as I say, both lucky and unlucky. And an interesting trivia: the Apollo 13's mission commander, Jim Lovell, was 42 years old, which, as you know, if you are a fan of the Hitchhiker's Guide to the Galaxy, is the answer to life, the universe, and everything. So you might want to say maybe there's a reason he was lucky and then got back safe. Now, the Apollo 13 crew coming back on this day in history was a wonderful time because, of course, whenever you see people sort of accomplishing these, seemingly impossible tasks, it's always a really inspiring. They did have a lot of experiments and scientific objectives they were going to trying to make if they had been on the moon. But just getting back was probably a victory enough. So I'll go ahead and say I definitely recommend both reading about the mission and the movie. It was quite good. And, of course, the extra props to the Saturn V rocket for getting them into a trajectory that could get them safely adjacent all the way to the moon. And fingers crossed, of course, for our new rockets and our new capabilities. Hopefully the Starship exceeds even the Saturn V capability. So fingers crossed on that one. All right. Now, anyone have any favorite Apollo 13 memories?
I'm afraid I'm too young. I don't really have any memories.
You've seen the movie though, right?
I think so. I definitely saw. Oh, I saw First Man. I don't think I saw Apollo 13.
Oh wow. Okay, I thought by now everyone had seen it, but maybe the movie is also too old.
That's possible. It's possible.
How about our guest, Dr. Kannan? Were you ever able to see the movie?
No, I haven't watched it. I've seen First Man as well, but not Apollo 13.
Okay. So apparently there's some movie competition going on, and Apollo 13 has lost out to First Man in this particular episode. I would recommend everyone to watch both of them.
Well, it's just I'm trying to watch them in order, so I have to watch First Man, and then I have to watch the second movie, and then I have to get to the 13th movie before I can watch Apollo 13. It's a bit of a long backlog, you know.
I'm not sure it's actually like a sequel, but I admire this program. All right, excellent. So let me go ahead and move us on to our next segment, which is very exciting. We're going to actually do a little bit of a guest talk by Dr. Rahul Kannan, who you've heard chiming in here in this episode so far, and I'm very happy to be able to introduce Dr. Kannan. He's a somewhat new, not brand new, but somewhat new professor here at York University. So he's an assistant professor at York University in the Department of Physics and Astronomy, and he actually studies some really interesting stuff. He's a computational astrophysicist working on modeling galaxy formation and evolution in a cosmological context, I should say, and has all kinds of thoughts about the properties of galaxies in plasma physics and all kinds of really interesting stuff, including even understanding the origin of first stars and galaxies in the universe. So probably more of an overlap with JWST type of interests. But Dr. Kannan, I'm very pleased to meet you here today. Would you please tell us a little bit about your research?
Yeah, Allan. Yeah, thank you. Thank you so much for the invite. Very delighted to be here. As you mentioned, I mainly study galaxy formation and evolution. I think, it's easy to, I think everybody knows what a galaxy is if you just look up at the sky. I mean, not today because it's dark and rainy in Toronto, but generally speaking, you do see a lot of stars, and almost all the stars you see in the night sky belongs to the Milky Way. You generally, if it is a clear sky and a clear day, and if you're away from the downtown core, and if you have a very nice view inside, then you can possibly see the Milky Way galaxy as well. You see it as a band of stars, as a high density band of stars. And that's, our sun is just one of these 100 billion stars that form the Milky Way galaxy that we live in. In fact, the sun is just an average star that orbits the galaxy. And it's, in fact, it orbits at about a distance of about 8 kiloparsecs. I don't know how you convert that into light years. Anybody know the conversion? Not sure. I think it's around 25,000 light years from the center of the galaxy itself. And the galaxy itself stretches far beyond.
Just FYI, you're almost exactly right.
I'm almost exactly right. Okay.
Yes. So eight kiloparsecs, you said?
Yes.
So I just checked it for you, and it is 26,092. So I would just like to say this is an extra good on the fly conversion from you, because I am super impressed.
Me too.
No, that's good. So we are quite a bit far away from the center of our own galaxy. And the sun itself is an average star, as I said previously. There are a lot of stars which are much more massive than the sun. and a lot more stars which are even less massive. So we are just an average star in an average galaxy, basically. But if you look a bit farther away from our own Milky Way, you'll see nearby galaxies with the naked eye, like Andromeda, for example. And if you're in the southern hemisphere, you might also be able to see satellite galaxies of the Milky Way, like the Large Magellanic Cloud and the Small Magellanic Cloud. The Andromeda itself is kind of a disky, kind of a structured galaxy. The Magellanic Clouds are unstructured because they're kind of interacting with each other and with the Milky Way galaxy itself. And if you go even a bit further, then you'll also see something called M31, which is a big elliptical galaxy. So the thing I'm trying to, say is that galaxies do not come in one shape or size. They actually come in very different shapes and sizes. And the point of doing this galaxy formation or studying the formation of galaxies is to understand how these galaxies form, how do they get their properties, and why do we see such a variety of galaxies near us. Okay. So there have been a lot of observations in the past 10 to 20 years or so, with basically using small-scale telescopes. They like the Sloan Digital Sky Survey, which is like a small telescope, I think, in Arizona. I'm not sure. These kinds of telescopes have mapped out the region around the Milky Way in quite fine detail, and they see hundreds and hundreds of thousands of galaxies which are close by. But what you also see is there's a lot of empty space in between these galaxies. So the universe is not just galaxy after galaxy after galaxy. It's galaxy, then there's some empty space in between, and then there's a galaxy at some other distance after that. So the question is why? Why is there structure, then there's no structure, and then there's some structure again? And the main reason why we think this happens is because the galaxies themselves form on top of the high density peaks in the matter distribution of the universe. So you have to think of it as like a distribution of matter in the universe, and where you have this large amount of matter or a high density of matter in the universe, you form galaxies in these density peaks. In fact, the galaxies, if you calculate the densities of these galaxies, they are about 1,000 to 10,000 times more dense than the average density of the universe itself. So the structures that we see around us, the stars, the planets, the galaxies, are all on top of these very high density peaks, whereas the mean density of the universe is much, much lower. Okay. But if you go back about 13.8 billion years ago to the start of the universe, about 300,000 years after the Big Bang, we can see how the universe looked like at around 300,000 years after the Big Bang. And we see that through something called the cosmic microwave background. This is when the gas cooled enough after the Big Bang so that the protons and the electrons basically combined to form hydrogen, and the photons or light particles basically decoupled from this gas. So what happened is that as soon as you have this temperature decreasing, you formed these atoms, and once you form these atoms, the universe became transparent to light. And so what you see in this cosmic microwave background is this, as the universe as it was 300,000 years after the Big Bang. So almost 13.8 billion years ago. So we have a very, very precise snapshot of how this universe looked like at this very early time, very early epoch in our universe. Okay. So if you look at this precise snapshot, called the cosmic CMB, you will see that it is extremely uniform. You don't have these structures that you see today in the universe. In fact, if you look at the temperature distribution of this cosmic microwave background, you will see that this temperature of this background is about 2.72 Kelvin to a factor of 1 in 100,000. So it's so uniform that the fluctuations are of the order of 1 in 100,000. Okay. So we know that the universe at this very, very early stage was extremely uniform. So the fluctuations of the order 1 in 100,000. How do this extremely uniform universe, how does that become this extremely non-uniform, clumpy universe with a lot of galaxies and nothing in between? So that is the question that I mainly work on. How do we form these structures of galaxies, structures in the universe like galaxies, stars, and planets? Okay. So the small fluctuations that you see in the cosmic microwave background, they are basically come from the primordial hot Big Bang of this universe. And these small fluctuations basically grow through gravity. So you have gravity, which attracts matter. So if you have a small perturbation, a small density peak in this very early universe, then gravity will keep attracting matter to this high density peak. And eventually, after 13.8 billion years of evolution or so, you will have galaxies that we see today. Okay, but this is, of course, I explained this in a very simple manner, but if it's much more complex, because this process is not just mediated by gravity, it's also mediated by other physical processes like radiation, magnetic fields, hydrodynamics, star formation, so you have to form stars, black hole formation, and feedback from these stars and black holes. And I'll come to what feedback means later. Okay. So what we can therefore consider galaxy formation as an initial conditions problem. The initial conditions, that is the density fluctuations in the primordial universe, is provided by the snapshot that is the cosmic microwave background. And what we are basically trying to figure out is how these initial small 1 in 100,000 density fluctuations grow up to become galaxies that we see today. And since the spatial and time scales involved in this problem are so large, so you have to, the time scale involved is about 13.8 billion years, spatial scales involved is about thousands of megaparsec, or I don't know how to convert that into light years. But anyway, so since the spatial and time scales involved are so large, you cannot perform experiments in a laboratory to figure out what's going on. So you need to rely on virtual experiments. And these are basically high performance computing algorithms that try to simulate this process of galaxy formation on a computer. So basically what we do is, instead of experiments in a laboratory, these are numerical experiments on a computer. So we write down the equations that govern the formation of galaxies, like the equations of gravity, the equations of hydrodynamics, the equations that govern star formation and feedback and black hole formation, all on a computer, and simulate it on extremely large scales. Okay. So first, as I said, the most important process that governs this galaxy formation or structure formation is gravity. The equations that govern this is quite simple, so it's very simple to model on a computer. Well, it's easy to model on small scales. If you want to go on large scales, if you want to model a large part of the universe, then you need to go to supercomputers to do this properly. The second important process that you need to model is hydrodynamics. That is basically the physics of how gas flows in galaxies, in and out of galaxies. By gas, I mean, most of the matter in the universe is composed of hydrogen and helium. And so they basically follow some kind of hydrodynamic equations that we also model on a computer. Okay. In addition to that, you also have to model processes like radiative cooling. So gas not only can interact through hydrodynamics, they can also lose their thermal energy by radiating away their energy as photons. So if a gas, some parcel of gas radiates away some amount of energy, then they releases the pressure and become much more dense, become more and more dense as they release more and more energy via this cooling. In fact, this is really, really important because the gas can cool to such low temperatures that it becomes so dense that you can actually begin to form stars. That's actually how you form stars in the universe. So you have this parcel of gas which cools due to radiative cooling, and as you cool, you lose pressure inside the gas, and then it becomes denser and denser and denser until you start to form stars. So that's basically how you form stars in the universe. So once you have stars, then the stars, through the process of nuclear fission, convert hydrogen and helium into heavier elements, and eventually, these stars, through winds like stellar winds and stuff like supernovae, they inject energy and these heavy elements like iron and carbon and oxygen back into the galaxy. Okay. So this is how most of the things that we are made of is formed inside the stars. So all the elements that are necessary for life on Earth was basically formed inside a star.
This is Science for the People. This week is all about physics.
So these stars not only eject these heavy elements back into the galaxy, as I mentioned before, they also, during this process of ejecting elements out in forms of supernovae, they also eject large amounts of energy into the galactic ecosystem as well. So what does this do? It kind of injects energy back into the galactic ecosystem, which stops the gas from other parcels of gas and nearby gas from cooling, which reduces the star formation in those parcels of gas. So what this does is kind of acts like a regulating mechanism to regulate the amount of star formation that you get in a galaxy. Okay, so stars regulate the formation of other stars. So the energy injection in the form of supernovae and stellar winds basically regulate how much stars you have in a galaxy. So if you want to understand and figure out how many stars can form in a given galaxy, or when do galaxies start forming stars or stop forming stars, you have to understand this process of energetic events like supernovae, which inject feedback back into the galactic environment and regulate this star formation process. Okay. In fact, there is also another process which regulates star formation basically in larger galaxies, which is basically black holes. So if you can get dense enough, or if you have massive enough stars which can form black holes at the end of their lifetime, then these black holes can basically accrete gas and grow their mass through this accretion of gas around them. Okay, and a certain fraction of this gas that they accrete, they convert this mass into energy and they release it back into the galactic environment. And we think this energy released from the black holes is also important to regulate the amount of stars in galaxies. So, especially in massive galaxies, in galaxies which are more massive than the Milky Way, we think that this kind of a feedback from black holes in the galaxy is really, really important in order to regulate the star formation in their galaxies. So as you can see, galaxy formation is quite a complicated process. You initially start with gravitational collapse. So basically you have these high density regions attracting matter towards itself, which increases the density around these high density peaks. And then and these high density peaks, the gas cools Once the gas cools and gets dense enough, it starts forming stars. Once you have these stars reaching the end of their lifetime, they eject both heavy elements like iron and carbon and oxygen and energy back into the galactic environment. This stops other stars from forming and thereby regulating the star formation in the galaxies itself. So I hope I have given you a rough idea about what galaxy formation in general means. I scan these things and then my and I put them up on my simulation. So the research I do mainly focuses on understanding all these processes using computer simulations. Why it'll be easy to get those first easier to get those. But of course, recently I've been more interested in galaxies, the first stars and galaxies that Allan talked about. This epoch is really interesting because this is the time when the very first stars and galaxies started to form. Okay, and this happened about 300 million years after the Big Bang. This was the first time when the gravity basically started making matter dense enough to form the very first stars and galaxies. Okay, and it is important and very interesting because JWST, which is the James Webb Space Telescope, which was launched about a year and a half ago or so, is basically one of the first telescopes that is able to peer into this epoch in a very nice way. Okay, so we already have some very nice observations of the galaxies at this epoch. In fact, we actually have some evidence that we see really massive galaxies even above redshift 10. So in the first 500 million years after the Big Bang, they are detecting galaxies which are almost as massive as the Milky Way. And none of the galaxy theories of galaxy formation predicted this. Okay. So my research currently is focused on trying to understand how these very first galaxies and stars
so why did you and your team decide that you
started to form and evolve in the very beginning of the universe, what their properties are, what do they look like, can we explain what JWST is basically seeing right now, because right now there are a lot of theories about why we are seeing such massive galaxies, but nobody has any idea about why this is. It might also be that the telescope is so new that we do not understand the instrumentation specific, or some of the data analysis pipelines are not well tested. So it might be that the discrepancy will go away once we understand the telescope better. But right now we are seeing very, very interesting clues into these very first stars and galaxies.
I really don't know.
I'm excited to do research on this in the coming months or so.
So what's your favorite? I am so glad. I wanted to say, first of all, this is an absolutely fascinating overview of the work you do, Dr. Kannan. Thank you. But I'm so glad that you brought up the JWST, because ever since the headlines about that came out, I have been thinking about it constantly. It's so interesting. All these ancient galaxies, some of the earliest galaxies in the observable universe, and they don't at all match what we expected. Obviously, I understand this is an emerging field of study, and one that we still haven't even performed all the preliminary research on. But I was wondering, could you maybe talk a little bit more about some of the possible explanations for why these galaxies are the way that they are? Any of the theories that you're testing, for example?
multiple fish.
Yeah.
So 20 fish at the same time. But when you can do that,
yeah, I will say a few things here. So first thing is when the first results came along, we thought that the cosmological, these galaxies basically broke the underlying cosmological model itself, which is the lambda CDM model that we talk about, because they seem to have so many stars that it was not possible that a galaxy had so much baryonic matter that it could form as many stars as you saw with JWST. Okay, but then people understood that this might be some artifact of the way they were understanding the data from the telescope itself, and so they have refined their estimates down. So now we have galaxies which are still quite massive, but not so massive that they break the cosmological model that we have, that is known to work very well currently.
That's really
okay,
cool.
so that's a good thing.
But
okay.
one
But
thing that I want to make sure
sorry?
I ask is, what are you all hoping that you'll learn?
Sorry, I was just saying. Oh, okay, that's interesting. I didn't know that. Please continue.
Yeah. So now we know that there aren't so many stars that it breaks the model, but there are these galaxies are still very massive. But as I said before, the process which regulates stars, the number of stars in a galaxy, or how massive a galaxy can get, is feedback from stars itself. We do not think black holes. Well, again, this is we are at a point where we do not know too much, so it might break. So our models might break. So, but we do not think black holes contribute too much to regulating star formation at this very early epoch. We think it's mainly stars doing the regulation themselves. Okay. So we have tested and we have created models for how these stars, especially supernovae feedback, like energy from supernovae from stars, regulate star formation in galaxies. And we have tested these models on galaxies like the Milky Way or galaxies up to redshift 2. So from about 6 billion years after the Big Bang to about 13 billion years after the Big Bang. So we have tested these models at late stages of the evolution of the universe. And what we have done is we have extrapolated these models down to about 500 million years after the Big Bang. And these extrapolations tell us something which
can you elaborate
which is discrepant with what JWST sees. So it might be that the way stars or supernovae regulate star formation in galaxies like the Milky Way, in present-day galaxies, is very different from how they regulate star formation in these very first early galaxies. Okay. So we might have to go back and revise our models of early star formation, early galaxy formation, in order to understand these new results. So we are trying to figure out what's going on now, but it's still in the very early stages.
Interesting. Okay.
Very fun stuff.
Yes, absolutely. I love this stuff. I always want to hear more about this.
Well, we're very lucky to have Dr. Kannan coming to York University. So now we get to have him tell us all about it. But yes, it's really, really fun, wonderful description of your research, and of course, telling us all about literally the entire universe is quite a lot to fit into just one little guest talk. But it is very fun, and I would like to just point a bit towards the incredible astronomical, if you'll forgive the pun, distances involved here as you go out to the very earliest points of the universe. You're going back a tremendous distance in space and also time. Do you at all worry about one of the sort of points of controversy I recall from years
to ask
ago
you a little
with
bit about how
distant
I
galaxy
read some articles
measurements
about
was,
how
of
your
course,
work with
errors
starting
in
fishes started,
redshift,
and
as in
you also
redshift,
mentioned that you use
redshift
hospital,
not being
CT
necessarily
scanners.
correct at large distances.
What was
Is that
that
something
like? Like, what was it like to
you worry
carry
about
dead
in
fish
your
into
models
hospitals
as someone
It's
who
always an adventure.
has
I mean,
now seen a little bit of a conflict?
My scanning career started out.
Yeah, so
I
these
took
it is
advantage
true.
of
So the early
folks
measurements
at
from
the
James
Shriners
Webb were
Hospital
mainly
and,
photometric
they had
redshifts.
a
So
separate
mainly,
procedure.
so they did not have spectroscopy. So they had photometry, which basically means you have
So they had a microscope
fluxes in certain large bands, and then you try to fit a model of light coming from galaxies to this photometry, to these images, and then try to figure out the redshift. And they generally can be wrong. You can confuse a very high redshift galaxy with a low redshift galaxy, but that's just dusty and it's dim because there is too much dust blocking the starlight. But recently, they also have this near spectroscopy instrument in JWST, which has kind of confirmed some of these high redshift galaxies spectroscopically. And these confirmed candidates still seem to be a little bit more massive, but just a little bit more massive than what theories predict. So the tension is not as bad with these spectroscopic candidates, I would say. But it's still there.
How does
But yeah, again, it's
investigate fish
really early days.
creative
So
in different ways than you wouldn't be able
hopefully
to
we'll get a
otherwise?
complete picture in a year or so, year or two. Yeah.
Yeah, it's a wonderful mystery.
Yeah, it's been nice. There have been so many papers on it in the past year. So as soon as there is a mystery, there's something to do for us. So that's good.
Quite often because I find holding something in my hand is incredibly helpful for
Certainly.
understanding it. Is I 3D print things. So from a CT scan.
Now, Dr. Hyde, I wanted to ask, you've got a note in here about ChatGPT. I'd really like to hear this question.
Oh yeah, yeah. So I thought we were going to take turns, but I'll ask my next one. So I was as you were giving your talk, of course, I'm reminded as one of the things in astronomy that we often have a lot of interest from is when we talk about the amount of computing and programming and advanced methods that we need to do for some of these kinds of analysis, especially some of the stuff that you're working on. We can't use just normal sort of write a computer program types of algorithms. And one of the things that has come up recently that is very much in the imagination and the usage of the public is, of course, ChatGPT. And you probably have heard people using it for all kinds of things that are wildly inappropriate. But that kind of technology, of course, using machine learning to extrapolate results from various databases, what I was actually wondering is how would you compare your high performance computing algorithms to something like ChatGPT? And just for fun, as that's something that a lot of people have actually seen recently.
Yeah, so it's definitely very interesting and fascinating to tack on AI to some of our simulations at least.
That's really neat about the sculpting.
As far as I understand how it works, is that you can kind of get
that
lots of fish.
Data out of noise, in a very sophisticated manner using if you learn, you need to train it on some ground truth. The point is, I do not know if you know the ground truth to train this thing on. I'm not sure. Maybe people doing AI will know a lot more than me about this. But the problem is, so if you want to understand how like a supernova interacts with this galactic surrounding stops and regulates star formation. So the way we do it is we solve the physical equations that govern this process. So if you have enough resolution elements in this kind of computer simulation, then you're kind of getting closer and closer to the truth. So there have been some simulations which do higher resolution using AI. So they go to, so you have a base resolution level set by the simulation itself, and then you go to sub-resolution using some kind of AI models. So that's very effective in, for example, simulations using just gravity, because we know how it goes on sub-resolution scales. But if you have models like hydrodynamics and star formation and feedback and stuff like this, then you already kind of approximate what's happening below the resolution level of the simulation using some models. And if you train your AI on that kind of models, then what I fear is that you might be training them to learn the model rather than learn the ground truth itself. So obviously, again, I'm not too much of an expert on this. There might be people who have much better ideas about how to do this, but
yeah, well, that's exactly what I put the question in for. Is I've spent some time in AI and ML myself, and one of the great questions we should always ask any of these routines is, why should I trust you? And we've seen so many examples of ChatGPT creating false truths from real-looking data when asked questions. So it will always return you an answer, but it might actually create completely false evidence for that answer because it has no ground truths for it. Right. And of course, one of the earliest AI puzzles was, if you put out in, I think, the 1950 or so, and I forget who did this, so maybe a little bit of a quiz for people, but there was someone who was saying, if you were to create a perfect AI program and you had, some military generals coming in and saying, tell me how to win the war, and the machine says yes, and the general says, okay, well, tell what's wrong with your machine? I'm a general, and so the machine says, okay, yes, sir, right? So they're not. And that's one of the points I always like to make on, I suppose, over and over again, is they're not smart like humans. They're smart like machines. And so, as you said, getting more data could potentially provide you with some ground truth. And we're all very interested to see what happens next, I think.
A coelacanth is that crazy.
Yeah, I mean, there, as I said, there have been
it definitely looks fishy.
Some progress in this, trying to do these higher resolution simulations using machine learning and AI, which is quite exciting, I would say, which allows you to get much better models by going to levels of resolution not achievable by the simulation that you actually have. But that's only if your processes themselves are kind of scale free, then you can go to resolution levels which are below your simulation. But if you have a process which is not scale free, then you have to train your models on simulations which go to that level themselves. So yeah, I mean, there's a lot of interesting stuff that you can do. Yeah, I think we'll just have to wait and see how good you can get. And I'm sure, by the way, by the amount of progress in the past just year or so, I'm sure there'll be a lot of progress in the next 6 to 8 months. Yeah.
Oh yeah, we're all looking forward to that hugely. So I wanted to make sure that since this is your first time over on York Universe, And since you're a little bit,
have
just arriving at York University a little bit ago, I wanted to make sure we actually got to talk a little bit about sort of your experience coming to York University.
Sure.
So I just wanted to, it's always interesting to talk to other people in science, how they've gotten to various places. What actually led you to York University in Toronto, and how long have you been here now? It seems my sense of time is completely out the window.
I've been here about 3.5 months. So I started January 1st this year at York. And it's been really nice. It's been great. I've been enjoying my teaching and research activities as well. And it was quite attractive for me to come here because the department itself is expanding quite rapidly and a lot of new faces, and I'm very interested to work with a lot of them actually, and most of the research kind of nicely blends in with mine. A lot of observers doing JWST observations, so I can provide models for them, theoretical models. And also the new hires that we are having this year also seem to be quite exciting. So very, very, very excited to be here. Yeah.
It is exciting. I just I recently got accepted to come back to York as a grad student, so I'm really, really excited to meet all the new hires that have come in since I left. Including you, especially.
Make themselves look about 4 times as big. But
I wanted to ask.
Sorry. Go ahead, Quentin. It's your turn. We've got time for maybe 1 or 2 more quick questions.
Sure. Well, since we're talking about studying at York University, how important do you think it is for current students to learn computing algorithms in astronomy? I remember when I was taking physics, it was taking some level of computer science was like necessary for the degree. But I took physics, not astronomy. I don't know to what extent it's required within the astronomy program. So I guess my question is like, how important is it if you're studying astronomy to learn these computing algorithms, and what kind of thing should you focus on if you're going to be going into astronomy in terms of computing?
It's really a neat thing.
Astronomy has kind of two to three kinds of aspects of it. One is observational astronomy, which you mainly deal with large amounts of data. Data analysis, data science is very, very useful in astronomy in general. Data science, including machine learning and AI, I think it's going to be the future for most of these large observatories, which are predicted to produce terabytes and terabytes of data per day. So, data analysis and data science is very, very, I think, necessary and useful. The other aspect is like simulations that I do. I think they're a bit more mathematical, hardcore computing algorithms and trying to understand, trying to write up computer code. Those kinds of things will be quite useful there. Of course, we also have these simulations that we run on these large computers, which also produce huge amounts of data. So there also data analysis is going to be quite useful. So these kinds of, I think it's astronomy and physics in general, nowadays it has become absolutely necessary to learn computing as well.
What's amazing about really paying attention in nature is...
Absolutely, of course. I would agree completely with that. I'm afraid we don't have very much time left in the show tonight. Do you have any last thoughts or things you'd like to add, Dr. Kannan?
There's an interesting problem.
No, this is a great program. Thank you for inviting me. I had a lot of fun.
Well, it's been wonderful having you on the show, and of course, as a quick last little thing, are there since we were talking about computing, what computing language would you recommend students to learn?
About a woman named
That's a difficult one. I suppose Python is quite useful these days. There are some people who use Julia and stuff like that. I haven't. I generally use Python and C and C++. But,
well, I'm glad to hear it because that's what I always tell people as well.
Yeah, same.
So you've heard it here again, folks, and everyone. I'd just like to take a moment to remind you that you have been listening to York Universe, the astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Quentin Wayrich and myself, Dr. Elena Hyde, and we've had on an amazing guest speaker, Dr. Rahul Kannan from York University, Physics and Astronomy. Stay tuned because it is Astronomy Night in Canada. Coming up next is Quirks and Quarks, Western World and Science for the People. You can always connect with us on Twitter at York Universe, and of course see our website at yorku/science/observatory for anything else you need. Thanks for tuning in. Clear skies and have a good night.
Watch it happen.
Good night.
You can't really believe that the thing isn't being drawn forward on a piece of string. I'll give you another example because it is a fish being drawn forward on a piece of string. Jimmy Liao at the University of Florida's Whitney Marine Lab did this spectacular experiment in when he was getting his PhD. He set up a flume